Thank you, and good afternoon. A more accurate account of the effect of K-space sampling and signal decay on the effective spatial resolution in fMRI. At 3 Tesla, we can image large-scale networks and cortical areas. 7 Tesla opened the possibility for imaging cortical columns and cortical layers. However, this is not easy. It requires planning and optimizing and interpreting and modeling fMRI at the resolution scale of cortical columns and layers. It is important for that to quantify the spatial specificity of fMRI and to analyze processes that degrade this spatial specificity. I'll first quantify the spatial specificity of the bold response relative to neuronal activity in humans. I'll ask what is the contribution of the imaging process to the bold point spread function. I will demonstrate limitations of the magnitude point spread function in accounting for the effect of K-space sampling and signal decay, and I'll present an alternative, more accurate model for accounting for the effect of K-space sampling and signal decay. Sorry? Do what? Like that? Okay. We quantify the spatial specificity using a point spread function of fMRI response. Of course, the bold response is cortical position dependent, as was shown by Logothetis et al., Krieger-Skorte, and Polimeni et al. However, quantification of the average tangential point spread function is useful for comparing spatial specificity of fMRI contrast and for planning, optimizing, and modeling. In addition, we quantify the point spread function associated with differential imaging, where the bold response is more homogeneous across space than in single condition imaging. Previous studies of the spatial specificity have demonstrated at 1.5 Tesla full width at half max, or 3.5 millimeter, at 3 Tesla 3.9 millimeter, and at 7 Tesla measured 2.34, and estimated smaller than 2 millimeter. All previous studies on the point spread function assumed a point-like neuronal response. However, neuronal responses are never point-like. Here I present scatter of receptive fields in V1 in monkey visual cortex, as was presented back by Hubel and Wiesel in 1974. So there is a spread of the neuronal response itself. So the objective of the first part is to estimate the point spread function of differential spin echo and gradient echo bold responses in humans at 7 Tesla while avoiding the neurophysiological spread confound. In order to circumvent the limits imposed by the scatter of receptive fields, we use the inherent cortical spatial organization for ocular dominance columns to determine the point spread function. We quantify the point spread function that best predict the spatial organization and magnitude of differential ocular dominance responses. In order to do that, we modified the model that we published back in 2011 for understanding the mechanism of decoding of cortical columns. The model is based on a Gaussian white noise patterns that we low-pass filter with an anisotropic kernel. This gives us a pattern which is very similar quantitatively to ocular dominance columns in humans, as shown here from post-mortem cytochrome oxidase. We simulate a response to left eye, right eye. We convolve with the bold response, and we simulate K-space sampling. We then fit the model to high-resolution fMRI of human ocular dominance columns at 7 Tesla that I obtained together with Isai Yaqub at the University of Minnesota. We constrain the model with prior probabilities of ocular dominance organization based on post-mortem cytochrome oxidase. So here we can see the spatial frequency, the irregularity, and the branchiness of the columns. And each iteration of the model, we take the model and the current parameters to estimate, to simulate an ocular dominance neurophysiological response. From that, we convolved with the bold point spread function and amplitude in order to get differential ocular dominance maps simulated, and we compare it to the data. And we ask what is the probability, given the parameters and the model, to obtain the data based on the currently simulated neurophysiological response. Here is how it looks. We'll show the several first iterations. This is data, differential ocular dominance, gradient echo. This is spin echo. This is the instantaneous Gaussian noise pattern and the simulated ocular dominance neurophysiological response. At the bottom, you'll see the simulated gradient echo response, differential response, and spin echo. And to the left, the full width at half max of the point spread function of spin echo and gradient echo. We start with a value of 2 millimeters. So quite after the very first iterations, the pattern converges to the pattern of differential ocular dominance that we obtained from the data, and the point spread function converged to about 0.8 and 1 millimeter for spin echo and gradient echo, respectively. So indeed, this is the results, the density function of the point spread function full width at half max for spin echo and gradient echo. We can see a 0.8 and about 1 millimeter. So I demonstrated the spatial specificity of the bold response, and this is now a really thin point spread function, about 1 millimeter, that brings up the question, what is the contribution of the MR imaging process to the bold point spread function? And we looked first at the magnitude point spread function to estimate this contribution, and I'll demonstrate actually limitations of the magnitude point spread function. So K-space sampling and signal decay affect the effective spatial resolution of fMRI and MRI. This effect is commonly assessed by means of the magnitude point spread function. The magnitude point spread function is defined as the absolute values of the complex MR imaging point spread function. It is assumed that the magnitude point spread function signifies blurring, which can be quantified by full width at half max. So let's see an example when there is no signal decay. The modulation transfer function describes the discrete sampling K-space. Its Fourier transform is the complex point spread function, and one can model the entire imaging process, as we did, by convolving the original pattern that needs to be imaged with the complex point spread function. Without any signal decay effect, the full width at half max of the magnitude point spread function is 1.2 voxels in our simulation. Similarly, for gradient echo imaging, we get now an effect on the modulation transfer function and the complex point spread function, the effect of signal decay, we can see it here, and the full width at half max is 1.3 voxels, and a similar result we obtain for 7 Tesla and readout duration of 27.8 milliseconds also for spin echo. Now, in order to test this against the reality, we simulated the complete imaging process. We simulated realistic pattern of ocular dominance columns with spatial frequency, a spectrum that shows a peak at 0.5 cycle per millimeter, as we demonstrated previously also in data, and we get from cytochrome oxidase staining. So let's see what we get. If we simulate the MR imaging process without any signal decay, the response and the spatial frequency spectra are comparable to those of the original pattern. So you can see here the blue curve, that's the original pattern. Red is complete fMRI simulation. However, the full width at half max of the magnitude point spread function is 1.2 voxels. And what we get if we convolve with the magnitude point spread function is reduced contrast in green and lower frequencies in the spectra. If we look at gradient echo imaging, we see actually slightly increased contrast. We see that the red curve shows higher amplitude relative to the blue curve, which is the original pattern, meaning that gradient echo acts as a high-pass filter. However, the point spread function, the magnitude point spread function width is still 1.3 voxels. That signifies blurring. Convolution with the magnitude point spread function in green reduces the contrast and pushes the spectra to lower frequencies. With spin echo imaging, we get a blurring, but however, this blurring that can be seen here in the red curve, the lower amplitude, is smaller than the effect of blurring of the imaging point spread function. So a substantial part of the width of the magnitude point-set function is due to the MRI sampling per se. Whether it results in blurring depends on the spatial frequency composition of the imaged object. Its effect can be neglected if voxels are sufficiently small with respect to the pattern. MRI reconstruction is typically followed by taking absolute values. Neither the complex point-set function or the magnitude point-set function describe this nonlinear process accurately. And lastly here, as limitation of the imaging point-set function, the magnitude point-set function, in addition to blurring, signal decay can also have a high-pass filter effect, as we demonstrated for gradient echo. This cannot be reflected by the magnitude point-set function. So I demonstrated the limitations. Now I'll demonstrate an alternative, more accurate model for the effect of K-space sampling and signal decay. We can approximate the complete process linearly. The entire process is nonlinear. We can simulate it linearly or approximate it linearly by calculating the functional derivative, meaning the derivative of the imaging process with respect to the pattern that needs to be imaged. This linear approximation is identical. It turns out to be identical to a convolution with the real component of the complex imaging point-set function. Here we demonstrate the errors, the relative errors, that we obtained with the magnitude point-set function. These are the green errors. We see relative error of about 50% for spin echo and 80% for gradient echo. However, with our approximation, linear approximation, we get errors that are close to 0. So convolution with the magnitude point-set function fails to approximate the true MRI process. Our derived linear approximation results in small approximation errors. The second stage is to fit a Gaussian, because in itself, the real component of the complex imaging point-set function is not very informative. Furthermore, it includes the effect of MR sampling per se. This effect is pattern dependent and irrelevant if the voxels are sufficiently small to sample the spatial frequency spectrum of the cortical columns. So we fit a Gaussian to the signal decay component of the linear approximation. Here for spin echo, you can see here in red the fitted Gaussian with the width of 0.89 voxels. For gradient echo, because gradient echo acts as a high-pass filter, we fit the Gaussian to the inverse MTF, as can be seen here in the red Gaussian and the orange function. The width here is 0.59 voxels. Here we demonstrate our approximation of the imaging point-set function for various total readout duration. And I would like to conclude by saying that the contribution of fMRI signal decay is small relative to the overall bold fMRI point-set function and can be further reduced by using sufficiently small voxels. So we demonstrated for gradient echo bold point function of about 1 millimeter, spin echo 0.8. If we take into account the effect of signal decay, it becomes 1.06 millimeter for gradient echo and about 0.7 for spin echo. Our proposed model is applicable to other fMRI and MR methods such as VASO and GRACE. We conclude that signal decay in spin echo fMRI with full K-space acquisition at 7 Tesla has a more moderate blurring effect compared to the effect implied by the magnitude point-set function. And we further conclude that in gradient echo fMRI at 7 Tesla has a high-pass filtering effect opposite to what can be expected from describing the effect of the magnitude point-set function. I would like to thank you for your attention.